Hello everyone. Welcome to the session on reasoning models. So we were discussing reasoning models, right? Specifically, the previous in the previous two lectures we discussed uh, different types of reasoning models, specifically in the training paradigm. So during training, how do you make this model so efficient for reasoning, right? So in today's class we will discuss a different aspect of these reasoning models, and specifically we'll discuss something called test time scaling, right? A test time compute, right? The idea is that we have done enough about training models with more data, more compute, more resources, right? New techniques and so on. But people have realized that there is a limit, right? Up to which you can achieve something, but after that you can't really actually progress, right, much. So we'll discuss today test time scaling, where we will see how this kind of reasoning methods models can be used in the inference time for generating better reasoning traces. So before that, this is today's breaking news. Some of you may know this model called GLM, right? This is another open source model, right, by Z.ai. This is a company, right? So GLM 406 version V were, this has been released in October 1, and it currently supports 200k tokens, right, in the context, and it was shown that this outperforms models like DeepSeek v3 v3.0 and Claude Sonnet 4 and so on and so forth. So another development in the open source community. So if you are interested, you can go through this blog and use this tool. So we'll discuss some of these datasets today. The datasets that they used for evaluating their models, like AIME dataset, HWE bench, right, and GPQ and so on and so forth. So these are the standard datasets that we generally use for evaluating these reasoning models. Okay, so let us briefly go back to the paradigm of scaling language models, right? Specifically scaling in terms of data sets and model parameters, right? So if you are asked to improve the performance of a model, the obvious response would be, okay, this is trivial because you just increase the number of parameters, right? And or right, you also increase the number of data points, size of the data set, right? And that would eventually capture all patterns present in the data set. So that's the obvious answer that all of us can think of. So the question that we ask here, can we just make them deeper? Can we just make the models deeper, larger, and and pre-train on large corpus, right? Would that be sufficient to improve the size or performance of the model, right? So there have been attempts to basically try to understand the relation between the performance of a model and all these all these aspects. For example, compute, right, data set size, parameters, and so on and so forth. Now if you look at these figures, right, so on the y-axis you see the test loss, right, and x-axis you see different aspects. Like for example, the first figure on the x-axis you see compute, right, in terms of pf days, right, and then second figure x-axis shows the size of the data set, and then the third figure x-axis shows the number of parameters. And as you see, as you increase the compute, right, petaflop, as you increase the number of tokens in the data set, if you increase the number of parameters in the model, the loss will decrease. And then Kaplan, so Kaplan and of course the colleague, right, so they proposed this law called Kaplan scaling law, and this is the scaling law that they proposed, right? So loss, right, so loss is essentially, loss will decrease if you increase the number of parameters. N is the number of parameters, right? If you increase the number of parameters, loss will decrease. If you increase the size of the data set, loss will decrease, right? And these are some of the coefficients that you need to set for a specific model. So what they did, they trained models with different parameter, different data sets, and they basically try to fit the data points, and they fit it using this power law, and they showed the relation between L and L, L and N, and L and D, right? So this is quite obvious, but later on, but if you think of it carefully, you cannot increase the number of parameters and the dataset size together. Why? Because you have a fixed compute, right? The compute is fixed, right? Now, given a certain compute, you can either increase the, let's say you have a flexibility to increase the size of the parameters as well as increase the size of the data, number of parameters and size of the data, right? So you can either increase the number of parameters, or you can increase the data set size, right? So later on, Hoffman from Google, right, and his colleagues, so they came up with the new law called the Chinchilla's law, right? And in the Chinchilla's law, they said that now this kind of power law is fine, where you see a relation between loss and a number of parameters, loss and the dataset size, but you also need to consider the fact that the total flops, right, or the total compute is fixed, right? Now, given this compute, either you can think of increasing parameters, or you can think of increasing the dataset size, and so on and so forth. So, and they showed that if you follow this kind of equation or the relation, right, they showed that their Chinchilla model, right, which is a 70 billion model, can beat their previous model, which is the Gopher model of size 280 billion, right, following this kind of law, right? So you should not arbitrarily increase the size of the models, you should not arbitrarily increase the size of the data sets, and so on and so forth, right? And then, a lot of follow-up works, took place after that. We recently wrote a survey paper on the scaling law in LLM. So if you're interested, you can look at that paper. We'll get a fair bit of ideas about what is happening in the scaling law paradigm. So now, if we try to improve the LLMs by optimally pre-training the models optimally, what are the problems? Right? The first problem is that, as I mentioned, the compute and training data are always limited, right? I mean, after all, you can only be able to scrape the entire website, internet, right? I mean, you can't go beyond that. Of course, you can think of going to people, collect data, record their voice, and so on. But the given data set that we have currently on the web, you can only collect scrape that data set. That's it. And compute is also limited. You can't increase this forever. The other problem is that if you think of synthetic data generation, right, or let's say duplicating data, right, that would be a problem, because you basically violate this IID assumption, right? Because now you are duplicating things, right, and your synthetic data essentially mimics the real world data, and you also see duplicates there also, right? And very importantly, if you keep on increasing the size of the parameters and data sets, that would affect the environment, right, in terms of CO2 emission, energy, and etc. etc. So if you look at this figure, x-axis number of parameters, right, and y-axis is the test loss. Left side y-axis is the test loss, and right side y-axis is the CO2 emission. As the loss decreases, CO2 emission also increases. Now this is true for the model size. This is also true for the data set. If you increase the data set, training data set, the same thing happens, right? So a statistic says that 10% improvement in performance requires 3x more energy. So the question is, do we really need to improve this 5%, 10% by compromising on the energy and compromising on the environmental effects and so on? So now during training time, how do we improve the model? We discussed many techniques in the past, right? But let's now look at the post training strategies, right? Post training meaning that your model has already been pre-trained, right? Now you want to fine tune your model, I mean, in the true sense, right? So that your model, produces the response that you want it to produce, right? For example, let's say without fine tuning, without supervised fine tuning, or without any usage of RL, you can just think of in context adaptation, where you can, in prompt you write examples, and you ask the model to perform similar kind of tasks, right? Following the examples. You can also think of supervised fine tuning, where you have this small data set and then you do fine tuning. Remember, these are all post training strategies. When I say post training, post pre training strategies, right? And of course RL for alignment. Now the usual approach is that we tend to give more weightage or more preference in the training time, right? So if you see the effort, and this is just a cartoon figure, if you see the effort, people tend to give more preference to the during the training time to improve the model, and give less preference to the test time, because people think that the model has already been trained, there is no point in doing further processing of the model, right? So if you follow the traditional approach, pre-training scaling, the participation across the globe would be limited. Why? Because people really do not have enough compute, right? If you ask me to focus more on training, right, I don't have compute, so I won't be able to participate. Who will participate? Those who have access to huge data, huge resource, right? Resource inefficiency, as I mentioned, data set is limited, GPU is also limited, and people also realize that performance has a plateau, right? So if you look at the performance, you see that after certain time, after certain scaling, you don't see enough growth, right? So even let's say for 1%, 2% improvement of accuracy, you actually need to put in a lot of data set, a lot of parameters, and update slowly. But as opposed to this, if you think of, let's say, putting in more effort during the test time, right, in the test time, so that not only increases the participation, right, across the globe, but also you may start exploring a new dimension altogether, a new aspect altogether, which has not been explored in the past. So this has been the direction of research in last 2-3 years, right? Specifically last I would say last 1 year, right? But since the invention of this chain of thoughts and tree of thoughts and stuff like that in 2022, 2023, people started thinking of test time scaling, right? Of course, the term test time scaling is very fancy. That was not there earlier. But if you think of COT, COT is also basically an inference time output, right? Because you just ask the model to think step by step, and the model is thinking step by step. There is no training involved as such. Of course, you can collect COT data, further fine tune it, right? And that can be possible. But in a zero shot setup, right, you just need to tell the model to think step by step. Okay, so why test time scaling is interesting? Because if you think of human cognition also follows the pattern called thinking fast and slow. Meaning that if a problem is complex enough, right, you think slow. If a problem is simple enough, you think fast, right? And models should also be knowing when to think, when and where to think fast, when and where to think slow, right? So, and there is this famous book called Thinking Fast and Slow. You can look at this. This is a very famous book of a Nobel laureate. So of course, now how do we achieve this thinking fast and slow kind of approach, right? One can say that I would do supervised fine tuning, meaning that I would collect data in such a way that the data set itself indicates where to think fast, where to think slow, right, where to wait, and so on and so forth. And that data will be given to the model for training, and the model should be able to understand where to wait, where to go fast, and so on, right? So there are approaches which basically talk about SFT and RL for this kind of fine tuning. So in general, when I say test time scaling, this is essentially indicating assigning more compute to enhance reasoning abilities inherently, right? Without keeping while keeping the model parameters fixed, right? So we'll discuss two types of methods. One type of methods focus more on prompting, right, less on fine tuning, and other kind of methods focus more on fine tuning, less on prompting, right? Now when I say fine tuning, you can ask why this fine tuning comes under test time scaling, because you said that in test time scaling there is no training as such. So SFT, RL are all post training approaches, right? So you can also think of, I mean, of course these are not inference time approach, but you can also think of these as non pre-training based approaches, right? So so therefore these things can come under test time scaling. So recent methods like DeepSeek R1, OpenAI's O1 model, these are all reasoning models, and these models also follow test time scaling abilities, right? We'll discuss this one by one. Okay, so before discussing the approaches, let us look at the empirical motivation. So in this figure, you see that so the first figure on the x-axis, you see the training time compute, right, and y-axis is the accuracy, and the second figure, x-axis is the test time compute and y-axis is the accuracy. So in both cases the performance improves with the increase of training time compute. So when I say training time compute, what does it mean? Test time compute, meaning that I basically let the model think deeper, and the model will produce more tokens. I forcefully let the model think deeper. Okay, so if you increase the train time compute and test time compute, in both the cases the performance increases, right? But if you look at the slope, in case of test time compute, the slope is more more higher, right? This is higher than the slope here. This is one motivation. The other motivation is that in this paper they showed that if you let the model generate more reasoning paths, right, for different data sets, for different tasks, right, as compared to, let's say, greedy decoding. A greedy decoding chooses the best one, right? So as opposed to greedy decoding, which is the orange line, if you let the model think more, right, the performance increases. If you look at the accuracy, performance also increases, right? So these are some of the evidences that test time scaling actually is a good idea. Okay, so last two classes we already discussed reasoning, non-reasoning models. As we all know that in non-reasoning model, essentially the final goal is just to produce the final answer, right answer, right? And there is no reasoning or thinking as such. These are not thinking models. These are all autoregressive models. So basically the goal is to predict the best next token that can be possible, right? So these are non-reasoning models. Whereas if you look at reasoning models, the next best token prediction is not the actual aim. The aim is to think properly, right? And maybe if you think of it, I mean, if you think in parallel, if you have multiple parallel thinking traces, right, you then you have some ways to verify which trace is useful, and so on and so forth, right? So we have discussed process reward model, right, in last to last class. So we'll use this kind of process, I mean, some sort of reward models which would assess the quality of these reasoning traces. So and in the reasoning trace generation, right, these reasoning models also generate the thinking tokens, for example, weight, right, final answer, let me go back, and so on and so forth. We'll see various types of thinking tokens, right, that these models generate. Now the question is, who taught these models to think, or who taught these models to essentially generate this kind of thinking tokens? So there are two ways. Again, one way is that you do everything in context, right, where you have some examples, and in the examples you place these kind of thinking tokens and you ask the models to follow that pattern. on the other hand, you can also think of another round of supervised fine tuning. For example, the S1 paper, right, the budget forcing paper proposed by Stanford, right? They took a very small 1,000 size data set, right, 1,000 instances of data set, and they manually added these thinking tokens, right, and then they fine tuned the model with that data set, and then they showed that with only this much of tiny data set, the model first of all learned where to stop, where to wait, and so on, and it outperforms really big models, big in the sense like those models which consider a lot of data sets for supervised fine tuning. Okay, we'll discuss these things one by one. So test time scaling strategies are categorized into two buckets. The first bucket we will discuss what we ask what, and the second bucket we ask how, right? So what in the sense like whether we will do sequential scaling, or we will do parallel scaling, or we will do hybrid scaling. So in sequential scaling, you basically force the model to think sequentially. There will be only one trace, there will be only one reasoning path, but the path will be deeper, right? In case of parallel scaling, you ask the model to think in parallel, right? There will be multiple parallel traces, and then there should be some ways to decide the best path, and hybrid is in between. So in some cases let's say you start with a parallel thinking, and then you realize that okay, maybe one path is doing good, so you keep on increasing the length of that path, and you forget about other paths, right? And when I say how, so as I mentioned, how, there are two ways. One is in context with prompts, right, and most of these methods basically follow prompts. And other is some sort of RL kind of approach, right, where you further fine tune with some RL in the loop. So let's focus on what first. Okay, so so in general, there are four types, as I mentioned: parallel scaling, sequential scaling, hybrid scaling. And so these are three famous approaches, right? Parallel scaling approaches like majority voting, beam search, right, diverse verified tree search, self consistency, these are parallel scaling approaches. I will discuss them briefly. Sequential scaling methods like self refine, react. I think react was taught, or no? It will be taught in the agent. So it will be taught in the next class. And S1 paper, S1 as I mentioned, TIP, these are the sequential scaling methods. And hybrid is in between, tree of thoughts, graph of thoughts, right, and so on. And then there came this new kind of methods called internal scaling. In internal scaling, what we have, so now so these methods, right, mostly all these methods are prompt based approaches, right? You write innovative prompts and you basically let the model follow those prompts and so on. But in internal scaling, you have some sort of RL loop which would decide how long one should think, right, or where one should stop, right, self-definement and all these strategies, right? Now DeepSeek, Urban, OpenAI's one paper, these, I mean, if you look at those papers, you get some ideas, but of course these papers are not very clear, right? If you look at if you read those papers, there are many things which are not that transparent, but the useful concepts. So if you look at the timeline here, GPT-3 came in 2020, and then COT was proposed in 2022, and then in 2022 these two parallel explorations started, parallel scaling and sequential scaling. Self consistency paper came in 2022 third quarter, and then star paper also came in 2022, right? And then process reward model concept was introduced in 2023, and then tree of thought was introduced 2023, right, MCTS, and then 2024 and 2025 O1 and R1 papers were introduced. Okay, let's start with parallel scaling first, right? Idea is that you generate parallel reasoning traces and then you choose the best one. So the first technique is very simple, best of n technique. So in best of n is a greedy kind of method. What you do here is that you use different types of prompts, or you can also think of let's say different ways of starting your thinking, right? But remember, this is greedy, okay, in the sense like it is not like beam search where you take top k. You know beam search, right? It's not like beam search where you take top k. Is greedy, so your initialization should be different, otherwise you will not be able to produce different results, right? So you start with different initializations, right, and you greedily explore the threads, right, and you have some sort of majority voting approaches to choose the best one, right? And generally here they do not use any process reward model. They don't use PRM as such. They only look at the final answer, and these are all like math types of questions. So these are deterministic answers, right? So among this n number of reasoning traces, if you see, you look at the majority output, right, and then you choose one of the traces which produces that output. Clear? Okay, now if you look at okay, so now also think of, you know, the probability of a successful trace. So if you think of P as a probability of a trace being successful, right, 1 minus P is the probability of the trace is not successful. To the power n is that all the traces are non-successful. 1 minus that is at least one of the traces successful. So you see that the probability of success is proportional to n. Now what is n? Number of traces that you generate, right? So it means that the more you allow the model to generate parallel traces, highly likely that you will be able to get the right answer. Beam search. Now beam search, all of us know, you start from a same prompt, and then you ask the model to generate k number of different tokens, right, and then you follow those tokens in parallel, and when we stop when the end of sentence is generated. Again, there is no PRM involved, right? So you stop when the end of sentence is generated, and then you do then again you do some majority voting. So later on in this approach, this is called diverse verifier tree search. So in diverse verifier tree search, they argued that beam search produces responses which are kind of similar responses, because after all what you are doing, you are taking the top k tokens, right, and top k tokens are kind of similar tokens, right? So the threads, the traces are not diverse, right? So what they did, they start with k diverse prompts, and these prompts are written manually, and they are actually diverse for a specific question, right? And then from each of the diverse prompts, they do exactly the same beam search kind of approach. So only difference is that they allow the models, and these are actually very light models, right, and there is no model as such, is all prompts. So so each of the branches would be very diverse, and then they also introduce the concept of PRM. So now there is no concept of majority voting as such. Now of course, if you think of PRM as just a majority voting, then that is fine. Otherwise, you can also train a process reward model to verify whether the branch is appropriate or not, right? Now remember, when I say PRM, I will not discuss PRM here. You know, discussed earlier. So PRM doesn't only consider the final answer. Now if it's a maths kind of reasoning problem, you can fine tune PRM separately, but it not only looks at the final answer but also looks at coherence, right, robustness, and many other small aspects of a reasoning trace. Okay, so we also did some experiment. This is our work, and we showed that among all the traces that we generate, generally the trace with the smallest length, right, is the trace which is accurate in general, right? Now these are empirical results. If you look at the correct, so you have correct responses, bunch of correct responses, bunch of incorrect responses, and you look at their length, right, and you plot the density of this length, right. So you see that incorrect responses tend to have less length, right, lower length, whereas correct responses tend to have lower length, and incorrect responses tend to have higher length, right. So this was our heuristics. Our heuristics is that what we do, we generate parallel traces, right, okay. So these are parallel sampling techniques. You generate parallel traces. Now remember, when I say parallel traces, essentially what we do is that it's, so you start with the first token, right, and let's say you know that I want to generate, let's say you want to generate 10 different traces, right. So you start, you generate first token for all the traces, and then second token for all the traces, third token for all the traces, right. You write your loop in that way. It's not like you first, you first create the first branch and second branch, and it's not like that, right. And then when you stop when this end of sentence is generated, right. Now the heuristics was that the reasoning trace which has lowest length would be the correct one. Now what is the intuition behind this? Now think of an oracle model, right. Let's say an oracle model, the model who knows everything, right, and the model which always produces the correct answer, right, it never produces a wrong answer. So if you ask a model, that kind of model, to solve a problem, generally the model will be very, very precise in terms of giving answers. The model would be verbose if the model thinks deeper, if the model is not very sure about the the output, the response, and so on. Let's say in case of human, right, if you are very clear about the answer, your answer will be very precise, right. You will not be descriptive, right. Of course, depends on the situation, but in general, right, you'll be very, very precise. So that was the heuristics. And it turned out that actually many models follow this kind of heuristics, right. And then we essentially had, and these kind of heuristics are also useful because if you look at the accuracy, right, it dramatically reduces the inference compute, right. Now you may argue that first finish search, the number of tokens that is required to generate in different branches, right, might be the same as the number of tokens generated in, let's say, majority voting, right, or budget forcing. Now what is number of tokens? The total number of tokens generated in all the branches, right. So if you fix that as your budget, right, that okay, you are allowed to generate up to 100 tokens, right. So there are two ways. One way is that you just create one branch with 100 tokens, or you, let's say, create 10 different branch with 10 tokens, right. Of course the branch size can be different, right. So we argued that specifically, if the question is easy, right, I should mention this, if the question is easy, then there is no point in doing this kind of sequential reasoning of 100 tokens, right. The model can generate things very quickly, and that would be your answer. Now these are parallel scaling. Now let's look at sequential scaling. So the first sequential scaling was proposed, I think, in 2023. Yeah, this is the self-refined paper, and the idea is very fancy, right. The idea is that you have a model M, you give an input, right, model generates something, and the model itself acts as a critic, right, and the model produces a feedback of its own output, right, and then the model refines its own output, right. Let's say the question is to generate the sum of 1, 2, 3 ... n. Initially the model produces this code, and then you and everything happens in terms of prompts, right? So you write a prompt and you ask the model to give a feedback on this output. The model will say that this code is slow as it uses brute force. A better approach is to use the formula dash dash, right? Now this is a feedback. This feedback will be given to the model and the model will refine it, and this is going to be the refined code. Now the question you may ask that if the model knows what's the efficient code, right? Why the model produced a code which was kind of inefficient at the beginning? Now remember, these are non-reasoning models, and the task was 2023, right? And the task was to generate next word properly, right? So model doesn't have any idea about whether the token or sequence of tokens that the model is going to generate would lead to an efficient result, right? So this kind of self-refinement process helped, and I will show you some results later on. Okay, now this is the budget forcing paper in this year, early this year, by Stanford, right? And this is also a sequential scaling approach. So the idea is that, let's say this is your task, okay? This is the question that you ask, and the model starts thinking, right? These are the steps, and then suddenly the model uses this token called weight, okay, and then think further. So model starts thinking, produces steps, and then the model returns weight, and then the model keeps on thinking on the same direction, right? And at the end, this is another token, final answer token, and then the model produces, this final answer. So look at here. So how many are in Raspberry? Okay, the model says, let's break down the process of counting the letter R in the word Raspberry. First letter R, this is an R, current count is 1. Second letter A, not an R, count 1, count remains 1. Sixth letter E, right, dot dot dot. Sixth letter E, not an R, count remains 1. Seventh letter R, this is an R, count 2. Eighth letter Y, not an R, count remains 2. The number of R's in Raspberry is 2. Wait, let's reread the question carefully. It asks how many R's in Raspberry, dot 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 dot, right? And then it says my initial answer was 2. Initial answer of 2 was incorrect due to quick reading of what? The final answer is 3, right? So what happened here? You forced the model to rethink, right? So now the question is, how do you force the model to rethink? And this is a sequential reasoning, remember. So what they did, they very precisely curated a data set of 1,000 instances, 1,000 traces, right, with this kind of special thinking tokens embedded. And then they just simply did an SFT, no RL, a simple SFT, right? And they showed that with this kind of approaches, the model automatically learns where to think. This is a very interesting paper, you can look at. And they call this method budget forcing because there is a budget. Of course, you can't think for infinite time. There's a budget, you can go up to that kind of budget and you stop, okay? And in that paper, they also showed that there is this concept of getting stopped or changing the gear arbitrarily, right? And the model actually produced that thing, right? So suddenly the model got stopped. Suddenly the model, produced this token weight and then started thinking again and so on. Okay, so follow-up work is this concept called thought switching penalty. Okay, now what is thought switching penalty? What is the idea? Again, this also comes under sequential scaling. So the idea is that, let's say when you start thinking, right, it should not happen that the model switches from one thinking trace to another thinking trace. It is okay to think in parallel, right? It is okay to think, it is not in parallel. It is okay to think in different directions because we do not know which direction will be useful. But it should not happen that let's say you are doing correct, right? Your thinking is correct, but suddenly due to this models, logic and other distribution, right, you suddenly shifted your thinking to another direction. It should not happen. So the idea is that they came up with the penalty. Now this penalty is imposed to this penalty is added to the logic, right? Let's say so far, again, hypothetically you assume that so far whatever you have thought, the confidence was very high, the probability was very high, right? At that time, if you suddenly start thinking in a different direction, or you produce a different token altogether, that is bad, right? If that happens, the model will add some penalty to the logic, right? Not only to the logic of that token, but also subsequent tokens, and you basically force the model not to think at that direction. Now it is completely okay that let's say your thinking was not going to the in a proper direction, and your confidence was very low, and then you switched. That is totally fine. But if your confidence is very high and then you switch, that is not allowed. So they came up with this concept called penalty strength. Now penalty strength is the amount of penalty that you impose to the logic of the token, so that kind of tokens are not generated, and penalty duration is the number of tokens for which you add this penalty. Remember, this is sequential scaling, meaning that again you have some budget restriction and you can go up to that budget. Now tree of thought is a hybrid approach. I will not go into details of tree of thought. I think it was discussed in the last year's class. I discussed it in the prompting section of last year, but this is again some sort of test time scaling. So the idea is that in tree of thought, you so you have something called intermediate thought units, right? Now what are these intermediate thought units? Now intermediate thought units are not, let's say in case of, let's say your task is to generate a poem, right, or generate a paragraph. So is the thought units are not characters. Thought units are not as small as characters, or thought units are not as big as the document itself, right? Thought units can be, if you think of them as a paragraph, for example, right? And these are vague concepts, right? So what you do, you start with a prompt and you ask the model. So this is a hybrid approach, right? You do parallel as well as sequential. So you generate intermediate thought units, right? And then for each, and these thought units are states, right? Now for each state, you generate k candidate thought using COT. You can do that, right? From each thought, you can just follow the COT kind of approach and you can proceed, right? Now the interesting part is the state evaluation. Now this is a bit tricky, and this is also not very clear in the paper. So what they said is that after every state, right, let's say in a branch there are 3 states that you already generated, right? After every state, you determine whether that branch would lead to the correct answer or not, right? And who will determine this? There is a separate language model, not the same language model. There is a separate language model, maybe a powerful language model. It will determine whether that trace or that branch would lead to correct answer or not. Okay, so this is a state evaluation, state evaluator. And once you generate the entire tree, then you have some strategy. The strategy can be a simple BFS or DFS, or let's say you have a score for every branch, and then you prune a branch which has low score and so on and so forth, right? And then you backtrack. Let's say you see that, okay, maybe you start with a high a branch with high score, you gradually move, and then you suddenly think that no, in rest of the states the scores are bad. You backtrack and you start exploring the other branch. The entire tree is generated by them. Okay. Now the major innovation is here, the state evaluation. Now, I mean, you can think of a process reward model. You can think of maybe another powerful model which now the kind of problems that they tried out. The problems are also deterministic problems. For example, let's say game of 24. Do you know this game? Huh? Game of 24. So you are given 4 numbers, right? your task would be to basically generate the number 24 by doing some operations with these numbers. Now you can use the intermediate results, right? For example, let's say you say that I will subtract 13, I will subtract 9 from 13 and 4 from 10, and then we multiply, right? So what you have done, you first subtracted this here and subtracted this one, you got some numbers and then you multiplied. So intermediate outputs can also be used to generate this number 24. Now what they said is that, and then again 5 cross 4, 5 cross 5 crossboard. Creative writing is of course something which is not deterministic, but other things are kind of deterministic. You know that whether a branch, or let's say if you ask a human being to verify whether a branch may lead to a correct answer or not, they should be able to verify this. Now let's look at the internal scaling, right? Specifically the O1 paper, right? O1 or R1 paper. I'll come to that. I'll come to the internal scaling, but let's look at the how question, right? So as I mentioned, there are two ways, right? One is tuning based. In tuning based, you do some fine tuning, SFT or RL, or the other one is more of an inference based, where you do stimulation, some sort of verification, search and aggregation. We discussed this. Stimulation is more of a self refining process, right? So I said, and the same model is used for refining and verifying, and then verification is O1, we'll discuss. Search is more of a TOT kind of approach, right? And aggregation is majority voting, first finish search, and so on. So let's look at OpenAI's O1 paper. Of course, this is a closed source model. I don't have much idea about what was there in the underlying this model, but overall this is the idea. So the idea is that O1 model was built on top of GPT-4. Okay, so GPT-4 architecture and reasoning focused pre-training. Remember, this is very important. Now the pre-training is reasoning focused, meaning that your data set, you have math questions, science question, code related questions, and there are also traces, right? So your focus is not to generate the next token, but to generate the correct reasoning, right? They fine-tuned on curated reasoning dataset, right, containing explicit thought sequence. Okay, to teach the model think before answering. This is very important, right? So in autoregressive model, the task was just to predict the next token, right? Those models don't think much, but here they think and then answer. They do RL, right, with some sort of reasoning rewards, and then they in their report, right, they mentioned this idea called internal reflection loops, adaptive halting. So what is this internal reflection loop? Name is very fancy, right? And these people know how to come up with fancy names. So internal reflection loops, meaning that the model itself tries to assess or reflects on the steps that the model generates, right? So you have self-reflection, right? And adaptive halting means the model knows where to halt, and this is determined dynamically, meaning that the model will understand that this is a simple question. The model doesn't need to think deeper, right? Doesn't need to think deeper, and the model can halt at any time. Whereas if the question is complex, then the model knows that it basically needs to think deeper, and it should not halt, and so on and so forth. And this is determined dynamically, right? And for adaptive halting, internal reflection loops, all these things are basically incorporated using RL, right? And it also has this safety alignment and so on, that we'll not discuss. But as I mentioned, test time scaling is an important factor in this kind of reasoning models. Okay, now let's focus on the evaluation of this reasoning models. So generally we use maths datasets, right? AIME and maths 500 is a popular dataset that we generally use, right? For the evaluation, these are Olympiad datasets, right? Maths Olympiad questions, right? AIME, the the answer is already given, and the model should be able to produce that answer. GPQA is more of an MCQ type of data set, right? But these are complicated data sets. GPQA has physics, chemistry, and mathematics. Mathematics questions, right? Whereas SWE bench is a code generation data set. So this is a leaderboard that people generally follow. Okay, now how do we evaluate these models? Remember, evaluating a reasoning trace and correctness of a reasoning trace is not explored yet, right? People have been thinking about it, but there is no concrete way to evaluate whether reasoning trace is correct or not. But there are ways to, there are proxies to actually evaluate the reasoning trace. For example, you can evaluate a model in 4 dimensions. The first dimension is performance. You look at the accuracy, right? And then you value, and then you measure the performance. So accuracy, what is pass at k? Pass at k is, let's say you have generated n different traces. You look at top k traces and you see is it kind of precision at k, right? You look at top k traces and see whether it is correct or not. Performance is pretty straightforward, but let's look at controllability, scalability, and efficiency. Controllability evaluates whether the test time methods can consistently adhere to the predefined resource constraint. What does it mean? Let's say your budget is something, right? You will check whether the reasoning trace generated by the model follows that constraint or not. A very simple idea. Let's say in this metric, control metric, it measures fraction of test time compute values that stay within the given upper and lower bound. So you have an upper bound of the reasoning trace that you should generate, the number of tokens that you should generate, and also the lower bound, right? So you check for how many traces it follows this, it basically ranges, or it comes within the range of this upper and lower limit, right? If it is okay, if it comes within this range, then it is okay, otherwise not. You can also look at the mean deviation from the target length. Let's say in your gold reasoning trace, let's say you have a gold reasoning trace, n is the length of the trace, and this is the length that you generated, right? Now you look at essentially the mean of this difference, and then of course RMSE, right? The same quantity RMSE. Clear? Is it clear? Now scalability. So in scalability, what we look at with the increasing number of tokens, right? Let's say you have 2 reasoning traces. One trace has length 10, another trace has length 15, right? Now what is the accuracy of a trace with length 10? What is the accuracy of a trace with length 15, right? So the numerator is the accuracy of these 2 traces, and the denominator is the length difference. So the idea is that with the unit length difference, whether the accuracy also scales accordingly or not, right? It is pretty straightforward, and you do this for all pairs of reasoning traces. So this Carly A has all reasoning traces, and then you take a pair of reasoning traces and you do the same. Now this is more of a quantitative approach. More qualitative approach is that you just draw a curve where x-axis is the compute and y-axis is the performance, right? And you analyze that curve. Okay, the third one is efficiency. In efficiency, you look at so total compute is basically the total number of tokens used across all generated responses for a given problem. As I mentioned, right? Let's say you have a majority voting kind of approach and let's say budget forcing kind of approach. In majority voting, there are multiple parallel traces generated. You see total number of tokens generated by all the traces. And here, in case of sequential trace generation, let's say budget forcing, you look at number of tokens and you compare which one is higher. If it is higher, it is bad. Sequential in sequential compute, you do not look at all tokens, you just look at the you just focus on that branch or that reasoning trace which is correct, right, and the corresponding tokens present in that specific branch, right. That can also be considered. Okay, the third one is very interesting. The third one is called underthinking score. What is underthinking score? I'll discuss this formula later, but first understand the intuition. The intuition is that you start with considering only those branches or only those visiting traces which are incorrect, right. You do not look at the correct responses, you look at incorrect responses, right. And in the incorrect responses, you see, in the incorrect responses, it may happen that some tokens, let's say some steps were correct, right. It may happen that in that incorrect response thread, initially you started thinking correctly, but then you got deviated. Other case, you never started thinking correctly. Now, other case, initially your thoughts were incorrect, then some correct thoughts, and then again incorrect, right. These are three cases. First case, initial thoughts are correct and then incorrect. Second case, all the thoughts are and when I say thoughts, steps, right, all the steps are incorrect, and these are all incorrect traces. And the third case is that incorrect, some correct, and then again incorrect, right. Which one is correct? I mean, which one is still okay? I mean, none of them are okay, but which one is okay? Maybe the first one is okay. Why? Because the model knows how to think correctly, but then maybe during the thinking process the model got deviated. Second case, the model was not able to think correctly at all. In the third case, after a long time the model started thinking and then again got deviated. So the idea is that the sooner you start thinking correctly, better it is for you. So what is TI? TI is the number of tokens in the entire trace, right? And what is TI cap? TI cap is the number of tokens till you generate the first correct step, right? Now think of a case where initially you generate the correct step. So T hat would be 0 or 1, or Ti would be the length, right? So this value would be small, values be small, 1 minus 1 would be very high, right? And that's the idea. And if the model is not able to produce any correct step, then what? Then Ti and T cap would be the same. The model is not able to produce any correct step, right? So Ti and T would be the same, 1 minus 1 would be 0. So the rest of things are pretty straightforward. So these are some of the results that I wanted to show. For example, if you look at self-consistency paper, self-consistency is majority voting majorly, right? I think I already showed this figure earlier, right? With the with the increasing number of reasoning paths, you see the accuracy increases, right? It is even better than greedy decoding and sample and rank decoding. In fact, in self-refined paper, this is the result of a self-refined paper, it also outperforms other approaches. Now this is the result of an S1 paper, right? X-axis indicates number of thinking tokens, right? Total number of tokens in the reasoning. Y-axis is the accuracy, and you see slope is pretty good, right? It's pretty high across data sets. They showed, as I mentioned earlier, they showed that if you look at S1, right, with only 1000 training instances or instances for fine-tuning, the model reaches an accuracy of 90-93%, which is equivalent to, let's say, a QWQ method, right, which required a lot of data set for fine-tuning. And in this figure, what we showed is that, so x-axis is the number of output tokens, y-axis is the accuracy. So if you do parallel scaling, so in the S1 paper they showed, if you do parallel scaling means parallel branches, right? The accuracy improves like this with the number of tokens. If you do sequential scaling, the accuracy improves like this. Okay, I'll not discuss all this. I'll finish here. Now let's think about it. Let's think about what we have discussed so far and decide when to use or where to use which model. Okay, let's look at this figure. Y-axis is the compute availability and x-axis is the task difficulty. Let's say if you look at this quadrant, you have less compute, and your question is easy. Which model should be used? FFS. Why? Because as I mentioned, if you basically don't need to think deeper, right? Maybe your small trace is the right trace, right? And you also don't have enough compute. Now let's look at this one. Low compute, difficult question. What do you do? Now FFS is parallel, remember, parallel scaling. What should we do? No, parallel scaling is useful when you have easy questions. Now for difficult questions, you should always choose a sequential model, right? So you can use budget forcing, right? So that the model thinks deeper. If you have high compute and easy question, then any model, right? If you have high compute and difficult question, you have a lot of computes, infinite number of computes. Parallel search, but which method? Majority voting. Majority voting is always good. Remember this, because you are actually generating multiple branches, right? All right, then let's look at the second figure. X-axis is the same, easy and difficult. Y-axis is model strength, the weak model and strong model. If you have a weak model and easy question, then FFS. Same reason. Weak model, difficult question, maybe BF, right? Weak model, strong model, difficult question, MB, and easy and strong, anything. Okay, so there is no silver bullet as such. You have to choose your model accordingly, according to your tasks. Okay, thank you.